Alright, so this notes video will be on arithmetic sequences. We have two objectives for this set of notes or learning activity. We want to be able to identify what an arithmetic sequence is by the end. We also want to be able to use and write explicit and recursive rules, which are like formulas, and we'll talk about the differences between an explicit formula and a recursive formula and how they relate to these sequences. So first of all, we have just the definition of a sequence. Think of it as a pattern. I'm sure you've dealt with these in previous math classes, but sequence has got like an order to it. We're listing off numbers and there's a certain pattern that's happening. It's a collection. It's ordered so that it has a first member, a second member, and a third member, etc. So, if we were looking at these sequences down here, our first member would be 3, second member 6, third 9, fourth 12. Next sequence, first would be 6, second would be 10, third would be 14, fourth would be 18, etc. All of these could have a number term, and then they also, have an actual number associated for that spot in the sequence. You may notice some patterns already between these sequences, and if you do, you can kind of make note of them. We're going to be getting into more specifically what makes something an arithmetic sequence, because there are different types of sequences that we'll encounter. Alright, so a sequence is an ordered list of numbers. It's a function. So a sequence is going to be a function. When I'm talking about the first term, the second term, the third term, those are our domain. And our range, our outputs, is going to be the actual numbers themselves in the sequence. So our domain is always going to be the set of consecutive integers, and what consecutive means is in a row. So let's make a note of that, next to the word consecutive. What that means in a row. And if it's integers, then it's going to be our whole number. So if it usually starts with 1, it'll go 1, 2, 3, 4, etc. Those are consecutive. All right, so next we have a term. A term is each number in the sequence. So when I'm talking about the first one, the second one, those are our terms. So we have a domain. Here's our consecutive integers, usually starting with 1. And these numbers are telling us the position of each term. So like I said, first, second, third, fourth, etc. Now, the range is what is actually the output. So, we have our first term, that's the input. Our output is getting the number 3. We have a second term, which is our input, and our output is the number 6. And the output, the collection of the range, is actually the sequence itself. So we're not always going to refer to the numbers 1, 2, 3, 4, 5. If we were just listing out a sequence, we would just see the set of the range. Okay, and so those were just, sequences in general. Now, an arithmetic sequence is a sequence in which the difference between the consecutive terms is constant. Or in other words, we have this number that we keep adding on to the previous term, and that gets us to the next one. So you may have noticed in our first slide that some of the sequences, that was their pattern. So if we actually go back, and here they are, which one do you think we would have just adding something to the previous term? So you can see here, if we start with 3, we add another 3, we get to 6, add another 3, we get to 9, add another 3, we get to 12. So we do have that common difference, that number that's being added on each time. We also see that in this next one, 6 plus 4 gets us to 10, 10 plus 4 is 14, and 14 plus 4 is 18. But you may notice that, this is not carrying on for every single one. From 2 to 4, that's adding 2. From 4 to 8, that's adding 4. From 8 to 16, that's adding 8. So the number that's being added on is actually different. So this would not be arithmetic, but the first two would. So let's get back to that definition. Okay, so when we say the difference between consecutive integers or consecutive terms is constant, that difference is that number that we're adding on. Basically, if I took the number 6 and subtracted the number 3, I would get that number 3 that I keep adding on each time. We're going to refer to this difference as D, and that'll be important because we use it in these formulas that we're going to be making. As we get more into linear equations, you'll notice that this consecutive difference ends up being a slope if we plot it, but I just want you to make that note for now. Okay, so here's for the rules. Now, if we were talking about just adding on that number each time, that's going to be following a recursive rule. So a recursive rule, it gives the beginning term, so it has to give us the very first one of the sequence. And then it gives us an equation to tell us how it is, how A of n, which is really just a term reference, and we'll get a little bit more into these notations, but it's how it's related to one or more of the preceding terms. So we're always basing the next term off of the term before, having to add on 3 each time. The way we will refer to terms, and this is our function notation. Remember, this does not mean f times n minus 1. I'm not distributing or anything here. This is f of n minus 1. Okay, so, we have f of n. We're referring to n because that's our nth term, and that's just a common thing in math. When you're talking about terms and their placement, you use the letter n instead of the letter x, and that goes with working with sequences. X is more dealing with lines, and n is more dealing with the nth term, what number of term, basically. Okay, so if we have f of n, that's just our current term. If we have f of n plus 1, that just means it's the term after this one. So if f of n is the 5th term, f of n plus 1 would be the 6th. And, at the same time, f of n minus 1 would be the 5th minus 1, which would be the 4th. But the way we could refer to them generally without saying the 5th or the 3rd is to, refer to it as f of n plus 1, and f of n minus 1. So this is just telling us kind of an order for things. So the way the recursive formula works is that the way we get our current term, so f of n, whatever term it is that we want, we have to take the term before, which is f of n minus 1, and we have to add d, this common difference. So I'll show you an example, but if you thought about, okay, if we wanted to find the second term, we would take the first term, and if our first term was 3, and each time we're adding on another 3, then my previous term plus 3 plus 3 would get me 6 the next term. To find the term after f of n, because it keeps going in order, we would take f of n, then add 3, and that's how we get, the one after f of n, which is f of n plus 1. So these are just really our function notations. We want to know the order that they're coming in. Obviously, if we're subtracting one, that's coming previously. If we're adding one, that's coming after. And this recursive formula is always telling us take the previous term and add that common difference. Okay, so decide if each sequence is arithmetic. And to decide whether a sequence is arithmetic, you want to find the differences of the consecutive terms and see if it's constant. So we want to see, are we adding on that same number every single time? How we could do that is, just to kind of go through marking. So if I take 1 minus -3, so I'm always going to take my term coming after and subtract my previous term, and this should be my common difference. So 1 minus -3, the double negative we would add, and 1 plus 3 is 4. So that means to get from -3 to 1, I have a positive 4, and you probably could have seen that without actually having to write out the subtraction, but just to show. And now I want to check if it's arithmetic. I should see that +4 throughout the rest of the sequence. I do see that from 1 to 5, we add 4. From 5 to 9, we're adding that 4. And from 9 to 13, adding 4. So yes, this is an arithmetic sequence in part A. I would like you to go through the rest of them and see if you're finding that these are arithmetic sequences before I give you the answer. So pause the video here. Okay, so here are the answers I came up with. And hopefully you did too. We could see that on B, we are adding a different number each time, so this one is not arithmetic. And then C, we are adding 3. You could also, show taking a term, subtracting the previous one, and we get the answer 3. So in part C, yes, this is arithmetic. Now remember to make the note that to decide, we need to find the difference of consecutive terms and see if it's constant. And by consecutive, we just mean terms in a row. So we should be looking at the difference between each term, how much is it increasing, or possibly how much is it decreasing. All right, so this is just another, reiteration of that kind of notation. F of 1 is the first term. The input is 1 and the output is 2. F of 2 is the second term, and that one is 5. F of 3 is the third term, which is 8, so on and so forth. We want to see, is this an arithmetic sequence? And hopefully you can notice or tell that yes, it is an arithmetic sequence because it increases by 3 each time, and therefore 3 is the common difference. So if we take that same sequence, same one as I have right here, so no need to rewrite it, and I want to write a recursive formula now. All I really need to do is, add in my common difference basically. So the common difference is the number that we are adding on each time, which we said was 3. And so to use the recursive formula, we need to take the previous term plus d. So we have f of 10. What would be the previous term to f of 10? That would be obviously f of 9. We said the previous term is always n minus 1. If this is my n, which is 10, minus 1 would give me 9. So I'm going to need to take f of 9, and I want to add on my common difference, which is 3. Now, I could go back up to my sequence and see which one was the 9th term. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 26 was my 9th term. So I'm going to take 26 plus 3, and that gives me 29. Now I could say that f of 10 is equal to 29. Then I can go on and find f of 11. Now, I know that it's really easy for you to add 3 to a number and keep going and going. What we're really trying to get down right here is the